that favorite time of yours, most probably the break time. So we will have a small one today, but hopefully enjoyable. Very soon, within a year or so, hopefully most of you will be graduating, and one of the best jobs that you can get around is what we are talking about here. One wife to the other. Where does your husband work? He is with oil and gas. See? PDO, Shell, Schlumberger. So, oh yes, oh great, great, great. Then, where is he based? Kitchen. Joke over. Now, we showed you one or two equations earlier, but now a little more about the mechanics of extrusion. The mechanics of extrusion. Here on this page, I am not showing you the slab method and the balance of the forces and so on, because now you know we have applied it in forging, we have applied it in rolling. So the same thing, the diagram is the same, right? There is the ram, there is the billet, this is the die, there is the original area of the billet A0, there is the final area of the extruded product AF, right, and so on. So based on that type of equilibrium, balance of forces and so on, the equations can be developed. I am directly giving you the equation. The ideal force, why? If there is no friction. In reality, there is no case where there is no friction. The friction can be very low, but if it is very low, then we can assume it to be almost zero. So if there is zero friction at the billet container interface, it means between the material being extruded, the billet, and the container wall. So then this portion of the force is ideal force. So the work of plastic deformation and the external work done. So a small p for pressure, a small u for the energy or the work done. Y, you know, is the flow stress, ln A0 upon AF. And we already defined that this A0 upon AF is known as the extrusion ratio. So Y ln R, right? So Y is the flow stress of the material at whatever load we are using it, and R is the extrusion ratio. So you can call it R or you can call it A0 upon AF. So under ideal conditions, when there is no friction, this is the pressure or the work done. Ideal force if there is some friction. So it is a 90-degree die, right? 90-degree die. When it is a 90-degree die, the material comes, hits the die wall and stops. More material comes, hits the die wall and stops. So there is a dead metal zone formed, And ideally, the material roughly starts to flow at a 45-degree angle and then goes there. So you can say that the extrusion angle, the die cone angle is 45 degrees, right? So that is there. Or if the die is 90-degree die, then the material internally automatically goes to a shear surface at 45 degrees. Remember, in solid mechanics and so on, when you were doing Morse circle and so forth, and you were finding the plane of maximum shear stress, it automatically comes out to be 45 degrees. So that happens here, that the material is being pushed, it hits the wall because the die is a 90-degree die. It cannot flow. But if more and more material comes, then a shear surface is formed at roughly 45 degrees angle naturally. So in this case, when the die is a 90-degree die, the force required or the pressure required will be high, but the material will still flow at 45 degrees. Or if the die cone angle is automatically 45 degrees, then it will flow at 45, but the force required will be low. So in this case, with friction, the pressure is Y 1.7 ln R plus 2L by D0. This L is the length of contact between the billet and the container. And this D naught is the original dia of the billet material, right? Or you can say that this L is the length of the billet, because initially the full billet is in contact with the container, right? So you, more technically, it is the length of contact between the billet and the container. After some extrusion, 10% extrusion has been done, the length has now decreased. There is less billet material remaining. After 50% extrusion, only 50% length is remaining in contact, right? So this L is a changing parameter. This is the length of contact. So before extrusion starts, at the start, this length is equal to the whole length of the billet. But after 10%, 20%, 30% extrusion is done, this length of contact keeps on decreasing. Okay? Y is still the flow stress. So here, extrusion pressure versus ram travel. As you keep on pressing the ram, originally the whole billet is there. Now I have pressed this much. Now I have pressed this much. Now I have pressed this much. So once I have pressed until here, now only this much length of the billet, the remaining length of the billet is in contact, isn't it? So because if you go back to the equation, that length of contact is in the numerator. So as the length decreases, the pressure required decreases, because in the beginning, the whole length of the billet is in contact with the container. So there is friction along the whole length. After 50%, friction is only with 50% remaining length, right? So the pressure initially increases. It reaches a maximum value and then it starts to decrease. This curve A, this red one, is direct extrusion. In indirect extrusion, it keeps on increasing and then it becomes constant. In indirect extrusion, remember, it goes back, so it is different. So the curve, initially this red one and then this one. So this curve is if there is a backward or indirect extrusion, but in forward normal extrusion, this goes like this. The pressure in direct extrusion is higher because of frictional resistance at the container billet interface, which decreases as the billet length decreases in the container, right? So if you go back to the diagram of direct extrusion or indirect extrusion, then you will see, oh yes, in direct extrusion, this is like this. In indirect extrusion, this is like this. Actual forces, those were sort of ideal forces. So to find the actual forces, there is an empirical formula. We have explained it. I have explained this word to you many times. This must have been explained in physics, this, that, lots of times. Equations are derived based on the mechanics of the problem, the physics of the problem. Then those are mechanistic equations. But if we do not understand the mechanics completely, it is very complicated. Then we do some experiments. And from the experimental results, we try to find an equation. If we do that, then it is called an empirical equation. Empirical means based on experiments, right? So rather than trying to do the mathematics based on the physics or the mechanics of the problem, we do many experiments, 10, 20, 30, 40, and then try to fit the experimental data to an equation. We know that the pressure equation is Y and ln R, right? So that is there, but they say we will do a linear type of it, A plus B ln R, A plus B ln R. And then for one type of material, one type of dye material and so on, we will do 2, 3, 4, 5, 6 experiments, and from the experiment we will try to find the value of A and B. So if these constants are known, then you have the equation. Y is equal to some number plus some other number ln R. Now R is the extrusion ratio, A naught upon AF, Y is the flow stress. So now you can find it. Typically in most of forward extrusion, A is around 0.8 and B varies from 1.2 to 1.5 depending on the cross-sectional shape of the die, on the billet material, on the temperature and so on, right? So if your company is doing only aluminum alloys and at certain temperatures, then there will be some guideline that in your company, if you are doing aluminum alloys at this temperature, then A is equal to say 0.8 and B is equal to suppose 0.1, 1.3, right? So it will be known by experiments. But this is the general thing, that A is 0.8 and B is between 1.2 to 1.5. If we want to find the extrusion pressure by this empirical formula, the Y and the R are real. This R is the extrusion ratio A naught upon AF. This Y is the flow stress of the material. A and B will be empirical. Optimum die angle, right? Remember, right? At low die angles, the force is high. At high die angles, the force is high. The curve is going like this. So there is an optimum die angle. So this optimum die angle depends on the total force, the ideal force, the force required for redundant deformation, the force required to overcome friction. So there are different components. I am not showing you all the equations, just to, in the book they are all there. There is an ideal force, then there is a force required for redundant deformation. It is the force required to deform the material. And then there is the force required to overcome the friction. If you add all of these, then you get the total force. So when you plot the total force, again the ram displacement, then you will see, then you, or against the, die cone angle, then you will see that there is a minimum. We will show you later on. Now again, if you have to find the pressure and so forth as a general equation, then I am reminding you of the general equations of materials, that plastic stress, this sigma is Y, K epsilon N. If you know the epsilon, the strain, true strain at any point, then for a given material, the K and N can be found from the tables in chapter 2 of the book, and you can find the flow stress Y. The average flow stress is K epsilon N upon N plus 1. And if there is hot work, then this Y or this sigma is C epsilon dot M. So I am just repeating the equations which we've shown you earlier in forging and rolling and so on, because this Y will depend on that, isn't it? I told you when I was explaining these for the first time that whether you are doing rolling or forging or extrusion, these general equations of material science will be the same. So what we were calling you the total force and so on is plotted here, that this is the extrusion force and this is the die angle. And you have A, this is the total, but B, C and D. B is the ideal force, it remains constant. C is the force required for redundant deformation, this C. So this is like in a direct proportion with die angle, keeps on increasing as the die angle increases. And D is the force required to overcome friction. So overcome friction, we have told you that as the die angle changes, this friction force decreases. So the total force is a combination of the ideal force, of the redundant force required for deformation, and of the force required against friction. So if you add at any point if you add this three, at any point if you add these three, this and this and this, then you will get the total force. So this is the total force variation. And now you have explained equation wise that extrusion force, total force against die angle. For lower die angles it will be high, for higher die angles it will be high, and for an optimum value we can find the optimum, right? So we will stop here today, and we will continue, and hopefully you will expend enough time in reviewing this material so that you really understand the basics of extrusion quite well, even without any derivations, direct equations. So thanks for today. We'll see you next time. Ma salama.